Today we are going to discuss the last point from this topic, that is thermochemistry, that is variation of enthalpy of a reaction with a temperature. This relation is also known as a Kirchoffs equation. Before starting this, in the last lecture we have studied about the resonance energy. Okay, resonance energy, for the example of taking the benzene. As far as the resonance energy is considered, again we can take the another example, that is the acetic acid. Acetic acid. Acetic acid having the two types of the values. That is, first is a calculated value, and second is the experimental value. Calculated value, that is equal to the relations like this here. That is, calculated value is equal to what? That is 330.8, and your experimental value is equal to 441.4 kilojoule per mole. Okay. Now, what happens here? What is the resonance energy? That is the difference between the experimental value and the calculated value. Whatever may be the difference between them, that is the resonance energy for this acetic acid. Now, what is the difference here? That is 441.4 minus 330.8. What is the remaining one here? 6, 0, 1, and here 1. That is 110.6 kilojoule per mole. That is the difference between the experimental value and the calculated value for the acetic acid here. Therefore, the acetic acid having the structure of a resonance is a more stable than the normal structure here. Okay, up to this we have the last point. Okay, now in the today's lecture we are going to discuss the variation of enthalpy of a reaction. Now, enthalpy of a reaction is depends upon the temperature. See here, enthalpy of the reaction depends upon the temperature. Okay, therefore we have, if we consider the reactions, that is reactant A gives the product, B products. Okay, at that time whatever may be the enthalpy of formation of a reactants is equal to enthalpy of formation of a products. But suppose delta H is the enthalpy of formation, here. Now, how can I write here for delta H? That is equal to what? That is H2 minus H1. H2 means what? That is of final products. That is equal to H2 of a products minus H1 of a reactants. Okay, H2 of a products of a H1 of a reactants. Now we have to differentiate this equation. See here, this is calling as equation number 1 here. Differentiating this equation, I am writing here that is differentiating equation 1 with respect to pressure at constant, with respect to a pressure at constant temperature, that is equal to, with respect to temperature at constant pressure, that is d by dt of, here we have to take delta H, okay, is equal to what? That is d by dt of a H2 of P minus what? d by dt of H1 of a reactants. Okay, thus this is the differentiating form of a equations. Now already we know that know that which quantity? That is known as a molar heat capacity at constant pressure and molar heat capacity at constant volume. What are its relations? Here, relations. Molar heat capacity at constant pressure, that is equal to d by dt of a h, okay, d by dt of h of p, okay, is equal to a Cp of a p, okay. Now this quantity we have to use here and we have to write this equation in this. Now using above Cp, therefore equation 2 becomes, here instead of d by dt of h, that is equal to enthalpy, that is equal to what? Here d of h is nothing but the delta h, okay. Therefore we can write here, instead of this we can read it as a Cp, okay. Now see here, that is therefore d by dt of delta h is equal to what? Here, what here I am writing here, that is Cp of, here at constant pressure, okay, of products minus Cp of a reactants at constant P, okay. Now Cp of products minus Cp of reactants, that is equal to what? Delta of Cp, okay, got it? Now delta of Cp, that is equal to add P, okay. Now here, see here, therefore d by dt of delta H is equal to this equation, equation number 3. Now rearranging the terms, we get that is, we have to turn what? This d2 along this, and this is a cross multiplication, okay. Now here what happens here? That is d of delta H is equal to what? That is delta of Cp, okay, into a dt, okay. This is called as equation number 4 here. Now we have to integrate integrating the above equation with temperature T1 to T2, okay, here, and from here and enthalpy change from H1 to H2 as limits, as that is integration of H1 to H2 here, d of delta H is equal to integration of which, that is equal to T1 to T2 delta of Cp of P into dt, okay. We know that molar heat capacity at constant pressure is a fixed one quantity, therefore we can take it out, that is equal to delta of Cp dash into Cp of P into T1 to T2 of dt. Here also the H of this, that is equal to this, that is equal to delta H of this H1 to H2 here, okay, taking the integration. Now Therefore, here delta H of H1 to H2 is equal to delta Cp into what? dt integration is what? T. That is equal to T into T1 to T2. Therefore, delta H2 minus delta H1 is equal to delta of Cp, okay, into T2 minus T1. Okay. Therefore, the final equation becomes, see here, what is the final equation here? That is, therefore, delta of H2 minus delta of H1 is equal to delta of Cp into T2 minus T1. Okay, this is known as a Kirchoffs equation. Kirchoffs equation here. Okay, here by using at which, that is variation of a enthalpy. Variation of enthalpy. Okay, what we have taken here? We have to first take the reaction A is equal to B. Then we have to assume the enthalpy of the products equal to reactants. Then take this their difference, and we have here the relation that is known as, this equation is known as the Kirchoffs equation. Similarly, instead of this delta Cp, if we can take, it is molar heat capacity at constant volume, we have the relation like this. In the last step, I can write here, that is, similarly, we can write here, that is delta E2 minus delta of E1, okay, is equal to delta Cp means Cv, okay, into T2 minus T1, okay, and this relation is also known as the Kirchoffs equation with molar heat capacity at constant volume, at constant volume, and here delta is equal to what? That is change in internal energy. Change in internal energy. Okay, got it? Thus, we have explained here variation of enthalpy reaction, enthalpy of a reaction with a temperature at, this is known as the equation enthalpy of reaction, that is delta of H2 minus delta of H1 is equal to what? Delta Cp into T2 minus T1, and in case, in the language of a molar heat capacity at constant volume, what? That is delta E2 minus delta E1 is equal to delta Cv into T2 minus T1. Thus, we have here concluded the topics thermodynamics along with a thermochemistry. In the next lecture, we are going to discuss some multiple choice questions with a answers one. So please concentrate on this derivation and becomes a practice one. Okay, thank you.